Okay, now let's pay some attention to what's called relativistic collisions. So what we have here is the collision between two particles. And assuming that the speed of these particles are not that small compared with the speed of light, then we call this collision event a relativistic collision. So we have to use relativity to study this collision. Well, in classical physics, the way we study collision, the cardinal principle we use was conservation rules, conservation laws, such as conservation of energy and momentum. And this still holds true for relativity. You know, we went out of our way to make sure that the new definition of the linear momentum still satisfied conservation laws when there was no external force. So we still have conservation of linear momentum in the absence of any external force, even though these particles can move at relativistic speeds. So this still holds true, linear momentum. What about energy? Well, we have to be a little careful here. This energy is not just the kinetic energy. It is rather the total energy of these particles involved. When you consider all the energies from this isolated system, energy is still conserved. All right. In classical physics, when we studied collisions, there was something implicit, and that is no matter what happens, the total mass of the particles before and after the collision cannot change. So we actually had a conservation of mass, and we use that implicitly. We just never changed the total mass before and after. Do we still have conservation of mass? Well, it depends on what we mean by mass. Are we talking about the rest mass, or are we talking about total mass, which has a gamma factor in it? Well, the total mass is proportional to the total energy. They differ only by a constant c squared. So if the total energy is conserved, so is the total mass. So gamma times m, the sum, will never change before and after the collision. But what about the rest mass? If you think of the rest mass, then it is certainly possible for the rest mass to change, because the rest mass can be partially converted into energy in the process. If we stick with conservation of total energy, then we can no longer insist on the conservation of rest mass. And the reason why in classical physics we have both conservation of energy and the conservation of rest mass was because the mass change was so minuscule that we didn't really have to consider that. But that was only an approximation, and that approximation may not be true anymore here in relativity. So let's take a look at this example. Suppose I have two particles. One has a rest mass m, and the second has a rest mass 2m. The first particle, the red one, moves with an initial speed, u initial, towards the second one. For simplicity, let's say the second one does not move before the collision. So there is a head-on collision between this particle and that particle. We can write the conservation of energy and momentum for this collision process. Again, for simplicity, let's assume the process is completely inelastic, meaning that as a result of the collision, you can form a single particle. They merge together to form a single particle, which moves with speed u final after the collision. Classically, we know that we can use conservation of energy and momentum. In fact, only conservation of momentum, not the conservation of kinetic energy, because this is inelastic collision. But we also can assume that the final mass of the particle, combined particle, must be 3m, because it's m plus 2m, right? That was conservation of mass. Can we still say the same thing here? Well, you'll see in a minute what happens. Okay, so let's apply conservation of momentum and total energy to this collision process. Conservation of momentum says initial momentum equals final momentum, and initial momentum is born only by this particle. So we have gamma u initial m u initial. That's it. That's p initial. And that must be equal to the final momentum. The final momentum is borne by that particle, and that particle has a certain mass. Classically, we know that certain mass is called 3m, but is that still true? I don't know, okay? I don't know. We call it capital M, whatever that is. And then this is the rest mass of the particle as a result of the collision, but it actually moves with the speed u final, and therefore its total mass is gamma u final times big M and then times its speed, u final. That is p initial, that is p final. Okay, so that's conservation of momentum. Now let's look at conservation of total energy. Before the collision, the total energy for this guy is gamma u initial m c squared. What about that one? That is, it doesn't move, so there's no gamma factor here, 2m c squared. Okay, that must equal to the final total energy, and the final total energy is gamma u final times m times c squared. That is conservation of energy and conservation of linear momentum. We have here two equations. How many unknowns do we have? Well, we have u final, and we have the total rest mass of the final particle, big M. If you assume big M to be the sum of these two masses, so you replace big M with 3 times small m, then there is only one variable left for this equation set, and that is u final. It is the only unknown. But you have two equations, right? You got two equations, only one unknown. What did that tell you? What if these two equations conflict with each other? Then we're in trouble. As a matter of fact, they do. If you plug in big M equals 3 small m, you find these two equations do not work with each other. They're not redundant, and therefore we have a problem. And that problem can be resolved by removing this assumption that the rest mass must equal to each other before and after the collision. So you leave big M as an unknown quantity. You can solve it along with u final, and then you will get your correct result. Some very simple algebra later, you'll find this is the final speed of the combined particle, and this is the rest mass of the combined particle. And let's see if they go back to the classical case. Okay, classically, the gamma factors all reach 1. So at low speeds, when u initial is far less than c, let's see what we have here. Gamma factor becomes 1, this gamma factor becomes 1, so this is ui over 3. The final particle has 1/3 of the speed of initial particle, and that makes total sense because the final particle has a mass of 3m, 3 times as large as the moving mass before, and therefore it must have only 1/3 of the final speed in order to preserve momentum. Okay? And what about the rest mass? Well, classically the rest mass, big M, is equal to 3 times small m, and that's indeed true. Again, if you take gamma equal to 1, that's 1 plus 2 over 1, and that indeed equals 3. So, same thing, this equals 3m. So we can go back to classical physics, but in the relativistic case, these factors do not agree with classical expression, so we have to be careful. We have to actually plug in the values of gamma ui, which we know because ui is known, and gamma u final, which also know because we know what u final is. So you see, we have still conservation of total linear momentum and conservation of total energy, but we are going to lose conservation of rest mass. As another example of relativistic collision, let's consider a situation where a photon of a frequency f strikes an electron. Now the photon, when it's captured by an atom, it simply disappears. It just converts into a burst of energy, so that can elevate an electron to a higher energy orbital, as we'll see in a later chapter. So photons can be converted into total energy. We're going to consider this following case. A photon comes in and strikes the electron. The electron absorbs all the energy and momentum of that photon. So as a result, the photon doesn't exist anymore. The electron will be energized, so it starts to move. It wasn't moving before. It starts to move with a speed u. So it basically carries all the energy and momentum of that photon. Can this event ever happen? And that is it possible for an electron in free space to totally absorb the energy of momentum of a photon? Well, let's see. If that happens, then you have to apply conservation of energy and momentum to the collision process, right? Before the collision, hf, that's the energy of the photon, and mec squared, that is the rest energy of the electron. It wasn't moving. And afterwards, there is only this moving electron. Photon is gone. Okay, here's the rest energy, and here is the momentum p of that electron. And from the energy momentum relationship, we know this is the total energy when a particle moves with with a momentum p. So that's the conservation of energy. And the next equation is the conservation linear momentum. The incoming momentum is from the photon is hf over c, and outgoing momentum is the electron momentum p. Now, we can easily combine these two equations. PC equals hf. So we replace PC with hf, and that's what we get. There's a square root on that side, so I'm going to square both sides. I can get rid of square root. Now, here's a problem. If you try to do that, if we call this A, this B, okay? Do you square it? That's A squared plus B squared plus 2AB, right? There is a cross term, which is 2 times MC squared times HF. That's the cross term. The other side is just A squared plus B squared. Again, this is A squared plus B squared plus 2AB. Here, this is A squared plus B squared. And A squared and B squared cancel from both sides. You're left with a cross term on the left-hand side that cannot be matched. The other side is 0. But the rest energy of the electron is not 0. Therefore, the only possibility is F equals 0. The photon has no frequency and therefore no energy. Therefore, it does not exist to begin with. What does that tell you? An electron can only absorb a photon with no energy, which means it simply cannot absorb any real photon. That's it. This event is forbidden because it does not satisfy both the conservation of energy and the conservation of momentum. An electron in free space will not be able to entirely absorb a photon. I have saved the best thing for the last in this chapter. We are now going to take a look at what's called paradoxes. Paradoxes in relativity. These are seemingly contradicting wrong results. Relativity, since its birth, encountered a lot of resistance from conventional wisdom. In the beginning, even most scientists, well-trained, highly trained scientists, did not believe it because it was such a revolutionary, radical idea. And when scientists gradually start to believe it, it is now an entirely established theory that is well agreed upon within the scientific community. But even today, relativity is a theory in science which still encounters a lot of skepticism and resistance, especially among science enthusiasts who are nevertheless not quite trained in this field. In fact, if you search the internet, you will find so many websites dedicated to what's called anti-relativity or counter-relativity. Those are the people who believe relativity was wrong, Einstein was wrong, and Newton's classical laws of physics still hold true, and because they believe something was wrong with relativity. And one of the reasons why they believe relativity was wrong was because relativity seemed to give people a lot of paradoxes, some contradictions. Well, are these paradoxes real? Well, by definition, the word paradox tells you it's only a pseudo conflict. It is not a real conflict. If you look at the situation carefully, it can be resolved. Okay? Relativity has such radically different ideas from conventional wisdom, and yet the assumptions are very simple, so that a lot of people thought that they can prove relativity to be wrong. But the reason why is because they did not study relativity well enough to realize it's a fully self-consistent theory, no matter how radical it is, no matter how different it is from conventional wisdom. What we're going to do is we're going to take a look at one of these paradoxes, the famous twin paradox, and see how we can resolve it. First of all, what is the twin paradox? Here's a setup of what's called the twin paradox. Let's consider two identical twin brothers, Homer and Ulysses. The textbook used two different names, but I think these names are more suggestive, don't you think? These two twin brothers, they look identical, and even their mother cannot tell them apart. But one day, Ulysses decides to board a fast-moving spaceship and travel to a star system, and then eventually come back. Homer, on the other hand, being Homer, decides to stay home. Now, here's where the paradox comes in. Homer can calculate the time it takes for Ulysses to go from here to there, from the distance between the two objects and also the speed at which his spaceship travels. And then it comes back. Let's say it takes a certain number of years to go this way and that way. Okay, whatever that number of years. So Homer says, it's been this many years since you returned, since you left, therefore I have aged by this many years. On the other hand, if Homer follows the motion of Ulysses through a powerful telescope, he can observe what Ulysses does on the spaceship, and since there's a time dilation factor, everything seems to be slowing down, right? Including the aging process of Ulysses. So according to Homer, by the time Ulysses comes back, Ulysses would look younger than Homer. Maybe even a few years younger. But where's the paradox? Well, the paradox lies in how Ulysses views what's going to happen. Ulysses says, okay, it takes me a certain number of years to go this way and come back, so I've aged this many years. But if I look at what happens on Earth through my telescope, I will find that Ulysses, everything is slowing down for him because of time dilation, right? Because he's moving relative to me. And therefore, he should have aged less by the time I meet him again. So therefore, Ulysses believes Homer would be younger, but Homer believes Ulysses would be younger. So the question is, as Ulysses lands back on Earth, you look at them side by side. Can you tell which one is older and which one is younger? That is the famous twin paradox. Okay, now how do we resolve this paradox? Let's give it some numbers, shall we? Let's say the distance between Earth and that star system is 8 light years, and that Ulysses travels with a high-speed flying ship with a speed of 0.8 c, and therefore, according to Homer, Ulysses would take 10 years to go from here to there, right? That would be 8 light years divided by 0.8 c. That's 10 years to go from here to there. And for simplicity, let's say Ulysses immediately makes a turn upon reaching that star system. So he doesn't spend any time over there. He spent another 10 years going back. So according to Homer, it's been 20 years since Ulysses made his way back, and therefore he himself, Homer, must have aged 20 years. But when Homer takes a look at what's going on with Ulysses through his telescope, he will find everything slows down because of time dilation, and therefore, how many years would he believe that Ulysses has aged? That would be 20 years divided by gamma factor, okay? And that gamma factor is 1 minus 0.8 squared. Okay, this is 1 over gamma, and so this is 1 over gamma. And this is 0.64, so 0.36. So overall, this is a 0.6. Okay, 0.6 times 20, that's 12 years. So Homer believes that Ulysses has aged only by 12 years because everything slows down, according to Homer's observation about Ulysses. So Homer says, I will be 20 years older, you would be 12 years older, and therefore I will look 8 years older than you. But Ulysses does not seem to agree with that. Ulysses says, look, I have spent a certain amount of time to go from here to there, but you would age less than that much time because, according to me, you are the one who is moving, and therefore you should age less by the same time dilation factor. So how do we resolve this problem now? Well, let's see. According to Homer, the distance between the two, between the Earth and the star is 8 light years, but not according to Ulysses. Ulysses experiences a different measurement because, according to him, the Earth and the star system are moving backwards, so the distance between them would shrink because of length contraction, right? It shrinks by a factor of gamma, and therefore the length L is no longer L naught. It is L naught times divided by gamma, and that is L naught times the same factor here times 0.6, and that is 8 times 0.6, 4.8 light years, according to Ulysses. The distance between these two, and he travels at a speed of 0.8 c, or rather the star closes in on him at that speed. So by the time he reaches that star, the time interval would be 4.8 light years divided by 0.8 c, and that's 6 years. So according to Ulysses, he would take 6 years to go from here to there. And since he made an immediate turn, he would take another 6 years to go back to Earth. So according to Ulysses, yes, he spent 12 years going back and forth. So indeed, he agreed with Homer that Ulysses has aged 12 years only. Okay, where is the paradox? The paradox lies when Ulysses tries to use time dilation to explain the aging process of Homer. According to Ulysses, that 12 years is the time spent according to him, but Homer would have aged less because Homer is in a moving frame relative to him, to Ulysses, and therefore Homer would have aged not 12 years but less than that. It's actually 12 years multiplied by that factor, 0.6. Okay, so that's less than 12 years. So Homer says, I've aged 20 years. Ulysses says, no, you have aged less than 12 years. That is where the paradox is. There are different ways to resolve this paradox. The way I like to do is to utilize the notion of Doppler effect. Let's assume that every year Homer sends a signal to Ulysses to mark the passage of 1 year. Okay, since Homer has to spend 20 years before Ulysses comes back, he would have sent 20 signals. And the frequency of that signal being sent is 1 per year, just for simplicity, 1 per year. Okay, so that's the frequency. But because of Doppler effect, Doppler shift, the frequency as registered by Ulysses is not 1 per year. As he moves towards the star system, he is moving away from the source, which is Homer, so he will receive frequency at a lower frequency. But as he comes back towards the Earth, he will be receiving this signal at a higher frequency than 1 per year. Okay, so according to Ulysses, what kind of frequency does he receive as he goes from here to there? Well, he is moving away from the source, so we have to use the Doppler effect formula, and that is f prime equals to f times 1 minus beta divided by 1 plus beta. That's when you move away. Beta equals 0.8. Okay, so this is f times 1 minus 0.8 divided by 1 plus 0.8. And you can easily do this algebra, this is f over 3. This is when he's moving away from the Earth. Now, when he approaches the Earth, we call it f double prime. All you have to do is reverse the sign of beta because now you're going this way instead of that way. And so there's 1 plus 0.8 divided by 1 minus 0.8, and that is just reversed, and numerator and denominator, you get 3f. Okay, so if f equals 1 per year, then on his way to the star system, Ulysses will receive frequencies at 1/3 per year. But on his way back, he will receive frequencies at 3 signals per year instead of 1 signal per year. So every time Ulysses receives a signal from Homer, he would agree that 1 year has passed on Homer's calendar, right? Because Homer sends 1 signal only every year. So all we have to figure out is just exactly how many signals did Ulysses receive. If Ulysses received only 8 signals, then he would say Homer has only aged 8 years. If he received 20 signals, then he has to agree that Homer has aged 20 years. Right? Okay, let's see. How many signals did Ulysses receive during his trip? Well, he spent 6 years going from here to there. During that 6 years, he's going away from the source, which is Homer, and therefore he received the frequency of 1/3 signal per year. That's that. So that is 1/3 of signal per year times 6 years. That's a total of only 2 signals before he reaches that star. Those 2 signals. So he says, okay, so Homer has only aged 2 years because I only received 2 signals from him. Now, he makes his way back. As he makes it back, he is facing the source. He is moving towards the source. So immediately he receives a higher frequency. What is that high frequency? The high frequency is 3 signals per year. And remember, he spent 6 years going from here to there. So during that 6 years, he must have received a total of 6 years times 3 signals per year. That's 18 signals. What is 2 plus 6 times 3? That is 20. So indeed, Ulysses received 20 signals from Homer. So he has to agree with Homer, and that is Homer has aged 20 years. Okay? So we have resolved part of this paradox, and that is, indeed, Homer has aged 20 years. Ulysses agrees with Homer now on that. Okay? But to completely resolve this problem, let's look at the other side of the story, and that is, according to Homer, how much older would Ulysses get? We use the same idea. That is, I want Ulysses to send Homer a signal every year according to his clock, to Ulysses' own clock. If Homer receives 12 signals, then he would agree that Ulysses has aged 12 years, just like Ulysses himself agrees on that. So let's see if that's the case. Ulysses, while traveling, sends Homer 1 signal every year. On his way from here to there, he spends 10 years, right? He spends 10 years going from here to there. During that 10 years, he sends a signal at a lower rate. Well, actually, he sends a signal at 1 per year, but according to Homer, the signal arrives at a lower rate of 1/3 per year. Here is the striking difference between Homer and Ulysses. Ulysses is the person who made that turn. Homer never did anything. But as Ulysses made a sudden turn, he would immediately face a faster frequency rate from Homer. But as far as Homer is concerned, the moment Ulysses made a turn, did anything change according to him? Would Homer even know that Ulysses just reached that star and made a turn? Of course he wouldn't, because that information, the fact that he made a turn, would have to propagate at the speed of light from here to there. Then Homer realized, oh, Ulysses has made a turn, right? And it's already been 10 years going from here to there for Ulysses. The signal that he sent right before he arrived at the star system will have to travel at the speed of light. That is the last slow signal. And that's going to take another 8 years to travel a distance of 8 light years. So it's been 10 years going this way, and another 8 years for the last slow signal to reach the Earth. There is a total of 18 years. During that time, the signal comes in at a slower rate of 1/3 per year. And the total number of signals received in the first 18 years of his trip, according to Homer, would be 18 times the rate of 1/3 per year. And that adds up to 6 signals. Okay, now Ulysses still has another 2 years, according to Homer, before he reaches home, right? And the last 2 years, the signals were coming at a faster rate because the last slow signal has already returned. And you got 2 years, and the signal comes in this time at 3 per year, and that's another 6 signals. So you got 6 slow signals and 6 fast signals within that 20-year span. And the total number of signals is 6 plus 6 equals 12. Therefore, Homer did receive no more and no less but 12 signals from Ulysses. So both Homer and Ulysses agree on the aging of each other. Okay, Ulysses believed that he spent 12 years on board, and Homer did receive 12 signals from him. So Ulysses must have aged 12 years according to both brothers. And Homer says Ulysses took 20 years to come back, so Homer himself has aged 20 years, but Homer, meanwhile, did receive only 12 signals from Ulysses, and therefore he has said Ulysses aged 12 years, but Ulysses received 20 signals from Homer, so Ulysses must agree that Homer has aged 20 years. Now I know that many of you will still shake your head and say, I don't buy that. Okay, even those numbers that you gave came out right, I still don't buy that. Because after all, isn't it true that the Ulysses system, the spaceship system, and the Earth system both inertial, therefore they're both equally good? So how come Homer wins the argument, Ulysses lost? Is there something really that breaks the symmetry between these two inertial frames, the flying ship frame and the Earth frame? If there is, what is that point that breaks the symmetry? Well, if you take a real close look, you find that in our argument, the moment when Ulysses made a sudden turn, that is where the problem arises. When he makes a sudden turn, he immediately faces a faster incoming frequency rate. And yet, Homer does not know he already made a turn, so therefore Homer has to wait a little bit longer before the faster signal comes in. It is the fact that Ulysses made a sudden turn that made the difference. That was where the symmetry between these two systems were broken. Ulysses always stayed within the same inertial frame. Homer has always stayed within the same inertial system, which is the Earth. He never accelerated. Ulysses, on the other hand, switched his reference frames from this inertial frame to that inertial frame. There is a brief moment when he switched these two frames. Even though that moment is brief, the fact that he did switch the reference frame from one inertial to another one, that fact is the one that breaks the symmetry between these two reference frames. So that's why Homer wins the argument and Ulysses lost.